Okay, let's look at lesson 81, comparing sound intensity. We will be able to compare sound intensity using decibels. So my goal in this lesson is to talk about the different ways we can compare sound intensity. Let's jump back to lesson 80 to see what we did. Lesson 80 and this lesson is also all about loudness. Loudness is how the amplitude of a sound wave differs. We know for quiet sounds we've got a low amplitude, for loud sounds we've got a large amplitude. Of course, one of the problems with amplitude and sound waves is that they drop off over time. Sound waves get quieter and quieter and quieter the further away you get from that sound. The reason is because that sound has to get spread over a larger area and it's going to lose some energy as it bumps into particles. I want to point out something that I didn't actually point out when I did this lesson, and even though I was thinking about it, I'm not sure if you guys remember, but a couple of lessons ago I talked about how sound underwater travels faster. I was actually sure in my head that if sound underwater travels faster, in my head I was thought that must affect the what that sound sounds like to your ear, and it turns out it doesn't. Yeah, sure, the wavelength will change, but that doesn't actually change how our ears perceive sound. But one thing that is true is that less sound is lost by when air particles have to bang into each other. They lose a lot of energy. That doesn't happen in water. So sound in water is actually louder. You can actually hear better underwater, sort of. Obviously, the problem with, well, at least animals that do live underwater can. The problem with humans is our ears aren't designed to hear underwater very well. And so when you hear something, it's actually that, but it still means that if you make a little quiet sound in water and a quiet sound in the air, you'll hear it a lot louder in the water. It's just, but our ears aren't fully equipped to deal with it, so it does get a bit murky, but it's interesting. It's an interesting idea. We talked about power and its energy over time, but then we talked about intensity, how it's power over an area. We solved an example that was very similar to the one we just did, except here they gave us the area straight up, whereas I told you guys to calculate the area, which made it a bit more challenging, but yeah. But a very similar question. Then we looked at the inverse square law. So instead of the area being A, what we did was we used the surface area of a sphere, because ultimately that's what's happening when the sound wave goes out. And that sort of links back to this idea here. It takes up a larger area. If you think about it, as that gets further and further away, the sphere of volume, the sphere of the sound is going to get larger and larger and larger. And so therefore, that energy is going to be spread out over a larger and larger area, and it's going to become weaker and weaker. So that means that the further you away, the quieter something will get. And then we did a quick example. Now, what we're going to do is we're actually going to explore that idea of the sound getting weaker and weaker and weaker. And I would like to actually explore that using mathematics. Okay, we're going to do that by using proportion. Let me show you how. We're going to use the inverse square law. Now, this is the first topic for today's lesson. It's new, so we're going to talk about it for a little bit. The inverse square law applies to sound, light, other things as well. But essentially, it's the same idea as what we've been talking about here. We can simplify this formula. How we simplify it is like this. Well, we know that 4 is a constant. We know that pi is a constant. So you can just sort of ignore those. And the power is produced by whatever's making the noise, whatever's making the light. So the power is almost a constant too, because you're not going to change as you get further and further away from an object. It's not going to change the power of the object at the start. It's just going to, change the power at the start is going to be same. It's a constant. So you can actually simplify this formula at the top into this formula here. I is, and that symbol, I'm not sure if you're familiar with that symbol, is called the proportional to. I, the intensity, is proportional to 1 on R squared. This is called the inverse square law, which states that as you increase the distance, R, the intensity decreases by R squared. Let me show you how. Let's take our position R. We're going to take our position R here, and we're going to take an area A. Now, as we go from R to 2R, we double the area, we double R. But even though we double R, what happens to A is it goes to 4 times A worth of area. Okay, it might be like 4 times A. That's the same as saying 2 squared times A. So even though we double R, we square the A, we square the area, we go 2 squared. What about when we go to 3 times? If we go from 1 to 3, we triple R, but A, the area goes from 1A to 9A. So we go from A, we triple R, but we actually go 3 squared A. So we go times 3 in the radius leads to 3 squared A, or 9A. So that's where the square part is. As you increase the radius or the distance from the point from 1R to 3R, the intensity drops off by a 1/9, not by a 1/3. And that's because ultimately what we're dealing with is we're dealing with area. I'm not sure if you guys remember, but I know that I spent a lot of time talking to my year 9s about it, and a little bit of time talking to my year 11s about it. But I remember talking about this idea that as you go from area, if you go from meters squared to centimeters squared, you need to times by 100 squared. So you have to make sure that because it's an area, same thing here, you're increasing it by a square. So if you increase your intensity is going to decrease by R squared, but if you increase the distance R away. This can have an important factor. So this is called the inverse square law. As I said, it applies to light, it applies to sound. It just means so that means that if you're listening to something and you move 2 meters away, if you move double the distance away, then you're not going to be hearing it's not going to be half as loud, it's going to be a quarter of loud. So let's just say you turn your speaker, let's just say you're at, let me just do this one more time. I've already done this like 2 or 3 times. Ooh, my screen is paused. What the? Hold on. Sorry. Hold on. Let me know if you have any issues and you can't see this, because I just had a bit of a malfunction with my Zoom stream, but let me know. But the idea is if you're listening to 100% volume at R and you go to 2R, you move twice as far away, you will be listening to instead 25%, not 50%. You have to go back. So you don't go back. If you go double the distance, your volume will go down to by a fourth to a quarter. And that's sort of how that sort of works. Someone's saying something in chat. I might disconnect randomly if my internet is acting up. So okay, fair enough. I've had some issues today with some students having bad internet or not being able to see me, so it might be my internet connection for some reason. Not sure, but if it is, let me know. So now what we're going to do is we're going to compare sound intensities. We can actually use this formula to our advantage. If we know the intensity, now that's not, by the way, saying we can calculate. This doesn't allow us to calculate the intensity. Proportional to doesn't allow us to calculate the intensity exactly, but it does allow us to compare intensities. I'm going to show you how. So let's pretend we measure sound intensity wave at two different distances. We can have I1, which is proportional to 1 on R1 squared, and I2, which is proportional to 1 on R2 squared. We can combine these formulas to make this. Now you can use an equal sign because you're just comparing two intensities. You've got two proportional twos. You can change into an equal sign if you compare two of them. So what you say in this is that you say that the sound intensity is of I2. If you know what I1 is and you know their radiuses away, you can actually find out what I2 is. So let's say, have I got an example? I have got an example coming up. So we're going to do an example in a second, but just a quick and easy example. Let's say you've got, let's just say I1 equals 1,000 watts per meter squared, and that's at 1 meter. Let's just say I2 is at, we'll go with 3 meters. Let's work this out. We're going to have I2 over, in this case, I1 is 1,000 equals R1, which is 1 meter squared over 3 squared. So that means we end up with I2 equals 1 over 3 is going to be 1 over 3 squared is going to be 1/9 of 1,000. So therefore, I2 is 1/9 of 1,000, which is going to be roughly about 100. 1,000 divided by 9 is 111. So that's what we can expect if we go to the 3 meter point. We should expect to hear this intensity. So we're going to do an example based off this formula here. This formula is just taking away the proportional two formulas, the inverse square. And again, as I keep saying, you can apply this to a light as well as sound. If you measure a light bulb to be 1,000 lumens, and which is a measure of brightness, or 1,000 watts per meter squared, and then you increase the distance away from that light bulb, same thing. Let's do this question. I want to try and get this done. If the sound intensity 3 meters away from the sound is 4 times 10 to the power of -6 watts per meter squared, what is the intensity at 1.5 meters, 12 meters away from the source? Well, let's do A together, and then I'm going to give you guys 5 minutes. I'm going to give you guys 3 minutes to do B. So we're going to do A together. So what we're going to do is we're going to say I1. We're going to say I1 equals 4 times 10 to the -6, and we're going to say R1 equals 3, because that's what it is, 3. Now what we're going to do with I2 is we're going to go I2 over I1 equals R1 squared over R2 squared. I'm just at the moment, by the way, I'm remembering this because I'm like 2, 2, 1, 1. So the 2s and the 1s are sort of like crisscrossing, because they're what do I mean by crisscrossing? I mean crisscrossing like that. But yeah. So now let's put in some values. I2, we don't know what the intensity is, but we do know what I1 is, 4 times 10 to the negative 6. We know that R1 is 3 squared, and we know that R2 is 1.5 squared. That means that I2 is going to be 3 squared over 1.5 squared times 4 times 10 to the negative 6. If I put that all in my calculator, I expect it to be louder. This is another general idea here. Because I'm moving closer to the speaker, I expect the number to go up. So I'm going to put this in my calculator now. 3 squared divided by 1.5 squared, all multiplied by 4 times 10 to the negative 6 gives me 1.6 times 10 to the negative 5. Yep, that's good. I was just like, what? Oh no, negative 5 is going to be larger than negative 6. Watts per meter squared. So it is louder. Beautiful. All right, guys, I'm going to give you guys 2 minutes to try and do question B on your own. Give it a go. See, someone's already given me an answer straight up, which is really good. I'm actually quite kind of happy with that. Give question B a try on your own, and then I'm going to go through the answers with you guys. So I'm going to give you guys 2 minutes on the clock. The time starts now. Just go. Oh, if you restart, it doesn't matter. 2 minutes, let's go. Let's get this answer done. I should actually really quickly do the answer too, but I will. Done. Done the answer. It was too easy. Calvin, I'm going to quickly let you know that you did get the right answer. He submitted it to me privately. All right, I've got another answer here from Fukli, and that one is also correct. Good job. Okay, third answer from Morrison. Good job, Morrison. Yeah, that's actually the correct answer. Excellent. You haven't included units there, but I don't mind too much you haven't included units. I would, but you know, all right. That's 2 minutes up now. Let's go through the answer really quickly in case you wanted to know how to do it. Super quick. And when I say super quick, I'm going to do this on the fly. Oh, and sneaking in at the very end, again, without units. Come on, we gets the answer correct. Let's power through this. How do you do this question? Okay, we're going to use the same formula here. We're going to substitute into this formula. I2 over, in this case, 4 times 10 to the power of negative 6 equals 3 squared, because that's what R1 is, and R2 this time is actually 12 meters squared, so over 12 meters squared. Punching that in gives me I2 equals 9 over 144 times 4 times 10 to the negative 6. That's going to give you 2.5 times 10 to the power of negative 7 watts per meter squared. And that number is smaller than this number, so that's a good sign that we got the answer correct. Because you're moving further away, so it should sound quieter. And that's the advantage here. We don't need to know when we use this formula, we don't need to know, like, oh, when we use this formula, you don't need to know the power of the speaker. You don't need to know, like, you don't even need to know the exact radius. You can just do double the distance and stuff. But you don't need to know the power of the speaker. You just need to, you're just comparing different distances. And that's actually a really useful skill to be able to have. Let's keep going, mate. Ladies and gents. So yeah, here we go. Decibels are another way to compare sound intensity. I don't actually have I actually don't have a picture here, which I'm actually kind of sad about. So how do we, where do decibels, why do we use decibels? What the heck are they? And we're going to have to show you a formula in a second, but we're going to start with this here. The threshold of hearing, this is the point where you can just hear something, is 1 times 10 to the negative 12 watts per meter squared. So that's the point where you can just hear something. And it's so soft that you would, to be honest with you, and it's also a young person, and it's so soft, by the way, that you might even think that you're just imagining a sound, but it is the threshold of hearing. The opposite of the threshold of hearing is the threshold of pain. This is the point where a sound is so loud that you cover your ears because it starts to hurt your ears that loud. The threshold of pain, and this is when your ears start to hurt. This is not, we're not talking about, you know, blood coming out of your ears pain. We're just talking about, hey, that's really annoying. Ow, that hurts. I'm going to cover my ears. That point is 1 watt per meter squared, which is pretty intense. If you can get 1 watt per meter squared, you're dealing with a very, very loud sound. So let's now look at the difference. And this is, by the way, for the same frequency. So we're not cheating and using different frequencies. This is both for 1,000 hertz and frequency. The difference between, and if you know, not many of you guys are doing general maths, but I know one of my general maths students is here. The difference between this and between this and this is a whole 12 units of magnitude. This is 12 units of magnitude, or 10 to the 12 times louder. 10 to the 12 times louder is actually a really big value. We're not talking about double, we're talking about 10 to the 12. We're talking about multiplying by 10, 12 times. So because this is such a big difference, what we tend to not use watts per meter squared. What people prefer to use is decibels. The reason we like to use decibels is because they are a log-based unit. If I've changed the slide too quickly, let me know. But this is the importance here. Decibels are a log-based unit. So that means that it's just like how something like the Richter scale works, or something like pH works. As you increase by 1 on this scale, you actually change by a factor of 10. It's actually a little bit different for decibels because of this 10 out the front. This 10 out the front actually changes it. So what that means is, as you go up by 10 in the decibels, you actually increase by a factor of 10, so multiply by 10. So the example I give for this is, if a sound goes up by 10 decibels, like from 90 to 100, the sound is actually 10 times greater in intensity. How can you calculate this then? How do you calculate something in decibels? What you do to calculate something in decibels is you use this formula here. So it's a log formula, just like you would expect it to be a log formula, where I naught is a reference intensity. It's usually the threshold of hearing, so 1 times 10 to the power of negative 12. And then you can use that to multiply by 10 to get to your measurement in decibels. let's grab a look at some of the examples here, and then what we'll do is I do our own example. So let's grab a look. Here's the threshold of hearing. That's got an intensity of 0 decibels. 10 decibels, the rustling of leaves. 20 decibels, purring of a cat. 30 decibels is a library reading room. 40 decibels is the sound inside a car with an engine on. Okay, so that's, you know, not loud, but it's at least noticeable. Conversation at a distance of 1 meter. Obviously, that's without wearing a face mask, but you know, but yeah. Busy street, 70 decibels. Jackhammer at a distance of 10 meters is 90. Siren at a distance of 30 meters is 100. So that increase, let's have a look here. This increase in 10 decibels is equal to 1 times 10 to the negative 3 to 1 times 10 to the negative 2. That's multiplying by 10. If you look at something, yeah, look here. Here's another multiplied by 10. If you actually look at, and yeah, times by 10, times by 10. If you look at something like from 30 to, actually go from 20 to 40, that's up by 20, so that means it's going to be an increase of multiplied by 100. And so that's how the decibel system works. Up by 20 is actually times by 100. It's a little bit complicated because of this 10. Normally in a scale like the PH scale or the Richter scale, an increase of 1 is the same as multiplying by 10. And what that does is it makes it easy because it's like, oh, that would be 100 equals 10 squared. What you got to do is you got to say, oh, the squared, that's what this 20 comes from. This plus 20 leads to 100 squared. So if you went from 10 to 40, that plus 30 is equal to 10 cubed, which is times 1,000. The 330, that's sort of where that comes from. It's a bit weird, but yeah. Let's do an example to get some ideas here. What is the intensity level of what is the sound intensity level of the sound intensity? What is the sound intensity level? Wow, geez. I copied and pasted this and I kind of, what is the sound intensity level of the sound intensity 3.6 times 10 to the negative 7 watts per meter squared? Okay, so how do we work this out? Well, we're going to use the formula, which is going to be the volume in decibels. We're going to do is we're going to go 10 times log 10 of 3.6 times 10 to the negative. Well, actually, let's do this properly. 10 times log 10 of I over I naught, which is the same as 10 times log 10 of 3.6 times 10 to the negative 7 over the threshold of hearing, which was 1 times 10 to the negative 12. 1 times 10 to the negative 12. Now, if I put this in my calculator, by the way, the log button, if you're not familiar with logs, it is just the button on your calculator that says log. For physics, that's all you need to worry about. You don't need to worry about the log laws or anything special like that. You don't even need to know how to convert. I don't think you need to know how to convert from a decibel into an intensity, but you know, which would be, of course, take the decibels, divide it by 10, and then take 10 rises into that power. We're not even going to deal with that. We're just going to deal with converting into this. So 10 times log of 3.6 times 10 to the power of negative 7, all divided by 1 times 10 to the negative 12. I'm actually going to put this in brackets because I'm worried that it'll just divide by 1 and then rise to the power of negative 12. So I'm going to put it in brackets just to be safe. Close brackets. Gives me 55.5 decibels. We'll go 55.6 decibels. Now, I would strongly suggest, by the way, ladies and gents, that if you're sitting here just enjoying the show, that you quickly whip out your calculator if you've got it beside you and do this yourself. I'm actually going to give you guys a minute just to do this yourself, starting from now. The reason I'm going to give you guys a minute just to do this yourself is just to make sure that you know that you're getting the same answers. Because if you're getting a different answer, then that might mean that you're making a mistake with your brackets and so on and so forth. And it'd be a really good chance for you guys just to check it out, make sure you're getting the right answers so that if you do have to do a question like this, you are certain that you know what you're doing. That's been about 30 seconds. I'm still going to give you guys another 30 seconds just to try this out. We could have rounded this up to 56 decibels. I think that would have been fine too. I just did, yeah, maybe I'll round it up to 56 decibels because because it's like this is two significant figures, so it makes sense that my answer should have two significant figures, not three. Also, by the way, ladies and gents, it's called, the deci is lowercase d because deci meaning a tenth, like a millimeter. A decibel is a tenth of a bell. That's where it comes from. By the way, decibels come from Alexander Bell, the person who invented the telephone. So that's where these units came from, if you're interested. One more example here, and that's going to be this one here. You can actually compare the loudness of two. I actually should have used the L symbol here. L equals 10, whatever, loudness. So here, you can actually compare the loudness of two different intensities in decibels. So let's look at this. What do I mean by that? And of course, what I mean by that is, remember how I said that the I naught is at the bottom is our reference? Well, you can make your reference, the reference can be anything. You don't have to use the threshold of, you don't have to use the threshold of hearing. You can use anything to compare the decibels, but if you use something other than the threshold of hearing, you can't say, oh, that's 20 decibels. You can only say stuff like, that's 20 decibels louder. So let's look at how you might do that in a question. This is going to be the last question that we go through today. At a fixed distance from the speaker, the sound intensity is measured as I1. This intensity is doubled to 2 times I1. So at a fixed distance, as fixed distance from a speaker, the sound intensity is measured as 2 times as I1. The intensity is doubled to 2 times I1 when a second speaker is added. So they bring another speaker in, and they add, and that, you know, doubles the intensity, which makes sense. You're doubling the power because you're adding another speaker, so that's going to double the intensity because power and intensity are linearly related. But how will that affect the decibels? Because decibels don't change with a linear rate. How does doubling the intensity affect the sound in decibels? We can actually calculate that. The change in the loudness is going to be equal to 10 times log 10 of I2 over I1. Now, I2 is 2 times I1. And of course, I1 is just I1. Now, hopefully you guys can see I've got I1 on the top, I1 on the bottom. That's going to cancel out. which is going to give me 10 times log 10 of 2 over 1, or just 2. That's something we can put into our calculator. So I'm going to put that into my calculator now. I'd suggest that you guys do the same. I'm actually going to get you guys to put down your answers in chat. Would love you guys to do the same and tell me what your answers in chat. I'm actually going to wait 30 seconds before I put the answer up, just so I can get you guys to give it a try in chat to see what you get. To just check that you're getting the right answers, because again, we're dealing with logs here, so you might not be getting the right answers. I've got an answer here. Okay, that's 30 seconds. I did not receive any answers in chat, but I'm going to put down the answer anyway because I want to make sure I do this. What we end up with is an increase of 3.01 decibels. So by using 2 speakers, right, your volume in decibels, your loudness in decibels doesn't go up double. It only goes up by 3. So if your loudness was 3 decibels at the start, then yeah, sure, it would double. But if your loudness was like 50 decibels, then you're only going from 50 decibels to 53 decibels. So decibels don't necessarily, yeah, if you double your volume in decibels, it's not the same as getting 2 speakers. And if you get 2 speakers, it doesn't mean you'll go from, if you get 2 speakers, it doesn't mean you'll go from 60 decibels to 120 decibels. If you get 2 speakers, you'll go from 60 decibels to 63 decibels, because we're going to go up by 3 decibels. If you added 10 speakers, you'd go from 60 decibels to 70 decibels, because you're increasing by a factor of 10, multiplying by 10. If you had 100 speakers, you go from 60 decibels to 80 decibels. But that's interesting. So that's something that you can calculate using this formula. And ladies and gents, that's all that I wanted to talk to you guys about with regards to loudness and decibels.